Guys, welcome to Calculus 1. This is our first session on Calculus 1. This is an updated version actually of the session. Today I want us to look at limit of a function. Okay, limits of functions. Okay, so now we are going to look at one of the most important concepts in mathematics. Okay, limits. we are usually given a limit in a form, a limit as x approaches a value a, where a is an element of real numbers, of a function to be equal to some value L. Okay, where L and A are elements of real numbers. Okay, which when I say L and A are elements of real numbers, I mean like they fall into the set of real numbers. Okay, they are real numbers by virtue. This is what happens, guys. Okay, how you interpret this, it actually comes to the idea that when x approaches a, the function of f or the y values of that particular function, they are going to approach L. It doesn't mean they are equals to L, they approach L. Why? Because we do not check what happens when the function actually gets to A. Okay, we don't check what happens when the function gets to A. We just check at the limit as x approaches A. We look at the function a value when that value of x is busy growing or decreasing towards the value of A. Okay, so the way you look at mathematics, guys, will really play a role here. Okay, so I want you to understand one thing. There are three basic ways, guys. This is the most important part of the video. This is why I made this video. That's why I updated the video actually, because at first I was dealing with each and every, but now I want to show you how to approach it in the most or the most effective ways of approaching a limit. Okay, now the ways to approach a limit are three. I'm gonna write them here. So the first one is numerical. Okay, let's say it's approach. So this one is when we use the tabular method. Okay, and the second one is graphically. Okay, let's just say graphically, and then approach. This one is when we use graphs, and then we have the last one, which is analytic approach. Okay, so this is when we use algebra. Okay, now fortunate enough, I do know all three ways of doing this, and I'm going to share with you the ways that you can see this. Your approach in mathematics is very critical. Okay, so how you look at how you view your problems or you view your questions really plays an important role in how you are going to answer that particular problem. Okay, now we're going to have three examples where we are going to see the numerical approach of that example, the graphical approach of that example, and the analytic approach of the same example. Okay, now before I move any further, I want you to understand something. Oh guys, I see that this thing looks like it's not clear, but I really hope you can see. This is analytical. Now I want you to remember something from a grade 12. Okay, since you are doing your calculus 1 from your grade 12, you must remember the most important functions that you used to do. The functions of parabola, the function hyperbola, and I want you to also remember the function or the inverse functions, actually inverse functions. Okay, all the inverse functions, doesn't matter if it's parabola, it's linear or what, all the functions, okay, the linear functions and stuff. Now, all of these functions, they're very critical, okay. Now, I'm gonna tell you one thing, guys. Your view in mathematics really plays a role or alters your approach in the limit, okay. Your view alters your approach. Okay, now I want you to understand something. So what I want you to understand is these functions, they will always be there, okay. How you look or how you view your questions or your functions will really alter how you approach your question, okay. Because if you're given something like this, a limit as x approaches a of a function, and you have to find what is that limit, how you view the function, especially if you're gonna do it graphically, how you view the function will alter how you approach the question. Let us have an example. Let us have an example. Let me remove this. Have an example here. Okay. So our example, they say we should find the limit as x approaches 1 of x minus 1 divided by x squared minus 1. Okay. So I do have my calculator with me for the first method here. So I'll try to move as quickly as possible. So let me just try to put this thing in motion such that we do not waste much time when we are doing our substitution of this thing, okay. Yeah, so let me just put empty brackets. You see, like there's nothing inside those brackets. So the first approach is the tabular method, okay. So the one that we said is the numerical approach. So we're gonna use the numerical approach. Now, the solution to this, okay, using the first approach, which is numerical approach. Now, I'm going to look at it from the perspective of okay, I don't want to give it away because this is gonna spoil the idea that I want to build from this. So let me not spoil it. Let me just try to do this because I don't want to make the video long. So I'll just solve one question and then I'll do follow-up videos solving another example, okay. So let us just go through this one. Now let me have values of x and have values of f at x, okay. So this is the table, okay. My pen is running out, guys, sorry. My pen is running out, sorry guys, sorry. Yes, this is our x, this is our f at x, okay. So since we are looking at x approaching that one, let us take it from 0.6, 0.7, 0.8, 0.9, 0.99, 0.999, okay. So we're going to take all these values, substitute, and see what's going to be the corresponding y values, okay. So with the 0.6, so I put it here. The first value we get is 0.625. So I'm going to convert it to two decimal places, okay. So it's going to be 0.63. So let's put 0.7. So 0.7 is like 0.7, guys, okay. You can write it as 0.7 or 0.7, it doesn't matter. So 0.59, and then let's look at 0.8, okay. So we put it here, 0.8, which is going to be 0.6 or 56, actually 56, let's put 0.9, we get 0.53, 0.53. Let's put 0.99, okay, 0.99, you get 0.50, okay, 50, and then let's put 0.999. It's going to be 0.50 again, 0.50. But now this is just because we are what do you call this, taking this to the nearest 2 decimal places, okay? That's why these two, they look the same, 0.50 and 0.50, but it doesn't defeat the idea. Now, do you agree that I was approaching 1 from the left here? Okay, we're approaching 1 from the left. Okay, from the left. So how am I okay, let me not get overexcited, and let's look at something. Let us approach 1 from the right. So we're gonna have x, and we're gonna have f at x. Now I want to make it a little bit bigger because I saw that it was not working so well. So let me put the first one, 0.01, 1.01, 1.1, 1.2, and 1.3, such that we don't have so much that you're going to, yeah. So now we do the same thing, we substitute 1.001, so we have 1.0001, and then we do the same thing, 1.0001, and then what do you get? 0.499999. So I can write it as 0.4999. Okay, this is the only one I'll make an exception from. Okay, let me check for the second one. If is this the only one we'll make an exception from? 0.4997. Okay, so I guess 0.4997. Let's check this other one. Do you see now what is happening here, guys? Okay, 0.498, 0.498. These are not the same thing, okay? And then let's look at 1.1 now, such that we keep the consistency going. So I get 0.48, and then let's put 1.2 here, and then we get 0.45, 0.45. So I don't have space for 1.3, but for purposes of you guys trying to see it, let's put 1.3 here. We get 0.43, yeah, 0.43. Now, this is when we approach 1 from the right. Okay, let's just write off 1 such that we know what we're talking about. Now, if you can look at this, when we're approaching, when x is approaching 1 from the left, y is approaching 0.5, and when x is approaching 1 from the right, f at x is also approaching 0.5, because 0.4999, if we can convert it to 2 decimal places, that's going to be equal to 0.50. Okay, if you can convert this to 2 decimal places, it's just 0.50. Okay, so thus if they approach the very same value, then we can say that therefore the limit as x approaches 1 of that function x minus 1, x squared minus 1 is equal to 0.5. Okay, that's the limit. Okay, so somebody might say, the tabular method is long, the tabular method is tiring and everything. It's fine, let us have the second method. Okay, I don't know if I'll have enough space. It's okay. Oh, I'll just it's okay, I'll make a plan. Now let us have the second method of doing it, which is the graphical approach. Okay, now we're looking at this one, which is the graphical approach. Now with the graphical approach, I want you to tell me if the function that I'm sketching, I was gonna use that space for something else, but it's fine. Now I want you to tell me if the function that I'm sketching now, is it mimicking or shows that function that was given to us, this one here, is exactly the same as the function that we are going to sketch right now. Okay, so that function is going to be the function of, so this is going to be x is equals to -1, and that function moves like this. Okay, that function moves like this. So we are going to look at x is equals to 1, and what is the corresponding y value when x is equals to 1. But what is this function equals to? This function is just the function of f at x is equals to 1 over x plus 1. And what type of a function is this one? Is the function which we have learned in grade 12, the hyperbola. Okay, so this is a hyperbolic function. Okay, this hyperbolic function has an asymptote. Okay, so the asymptote, it actually has two asymptotes, because this is +0, which thus we do have that horizontal asymptote and that vertical asymptote. Okay, so this function and this function are exactly equals to one another. It's just that here we multiplied by the complex conjugate, but if they're exactly the same. I don't want to explain a lot of things and stuff like that. So let us check what is f at 1 here. It's going to be 1 over 1 plus 1, which is 1 over 2. 1 over 2 is just 0.5. Okay, if you can see that, guys, you can see that, let's have this 1 over 2 here. When x is approaching 1 from this side and x is approaching 1 from this side, y from this side is approaching 0.5 and y from this side is approaching 0.5. Thus, we can say that the limit as x approaches 1 of x minus 1 over x squared minus 1 is equals to 1.5, which is 0.5. Okay, now let us look at the last way of looking at it. Now this is the last method or approach, which is the analytic approach. Okay, the one that most people like, the algebra one. Okay, now the limit as x approaches 1 of x minus 1 over x squared minus 1. Okay guys, sorry, this one writes with the very bold so I need to remove a bit of that. Sorry guys about it. So it's just x squared minus 1. Okay, so what happens is that we know that this shows us a difference of 2 squared. So x squared minus 1 is just x plus 1, x minus 1. Okay, so we're gonna take that idea and write it up here. So we will have this as, this is not the same approach. Okay, let me just separate that. So you're gonna have the limit as x approaches 1. At the top you have x minus 1. At the bottom it's x plus 1, it's x minus 1. And you can see that this and that, they give us 1. So you have the limit as x approaches 1 of 1 over x plus 1. Okay, and then thus we will have this as 1 over 2. So in all of the in all of the approaches that we chose, our limit is equals to 0.5 or 1/2. Okay, so guys, if you came this far, guys, please hit the like button, please subscribe, please share the video. I'll see you in the next one. Thank you.